So I will be the one who's going to discuss the illustrating net area from graphs. The net area concept in integral calculus deals with finding the total area between a function's curve, the x-axis, and the given interval. Areas above the x-axis are considered positive, and areas below the x-axis are considered negative. To account for their contribution, the definite integral calculates the net area, which is the positive area minus the negative area. This net area can be positive, negative, or zero. We find the net change, not just increase, by considering both positive increase and negative decrease area. Many real-world scenarios involve both increase and decrease, distance travel, back account balance, work done by a force. Ignoring negative areas leads to inaccurate calculation. Definite integrals give a signed value, um, positive or negative, to show direction of change, not just magnitude. So let's go now to the introduction to Riemann sums and regular partition. A Riemann sum approximates the area under a curve by dividing the interval into slices and summing up the area of rectangles that fit within those slices. Riemann sums are helpful tool for understanding definite integral, which give the exact area under the curve using the formula f sub x1 times delta x plus f sub x2 times delta x to f sub xn times delta x. In Riemann sum, a regular partition cut the interval into slices of equal. This is beneficial because it simplifies the math with constant width delta x for all slices. Calculation become more easier. It improves accuracy using more slices, increase subintervals, naturally reduce delta x, leading to a better approximation of the actual area. While irregular partition unequal slices are possible, they make the math more complex.
Good day everyone. So I'm going to discuss illustrating Riemann sums using graphs. Here's a step-by-step guide using simple example. So the function is fx is equals to x squared on the interval 0 and 8. So first step is graphing the function. Start by graphing the function you want to integrate. In this example, we have graphed the function fx equals to x squared on the interval 0 and 8. The curve represents the functions. Next is dividing the interval. Divide the interval 0 and 8 into subintervals. In this example, we have divided it into 4 equal subintervals, and that is 0 and 2, 2 and 4, 4 and 6, and 6 and 8. Vertical lines are drawn at the endpoints of these subintervals. Next is choosing sample points. Choose a sample point within each subinterval. In this example, we have chosen the right endpoint of each subinterval as the sample point. Drawing rectangles. For each subinterval, draw a rectangle where the base and the subinterval and the height is the function value at this sample point. These rectangles represent the areas under the curve for each subinterval. Coloring the rectangles. To make the Riemann sum visually clear, the rectangles are colored in. The sum of the areas of these rectangles is an approximation of the area under the curve, which is the Riemann sum.
So here's an example of table demonstrating the process of calculating Riemann sums for the function f of x is equals to x squared over the interval of 0 and 4 using three subintervals. At first, we divide the interval into three equal parts. Second, for each subinterval, we find the midpoint, calculate the width, evaluate the function at that midpoint, and find the area of corresponding rectangle. At last, summing up the areas of rectangles gives an approximation of the total area under the curve, which in this case is approximately 21.